Welcome to Demystifying Kubernetes Resource Management, everything you've always wanted to know. All right, I'm going to take this off for a second, but we're afraid to ask. Well, let's do this. So agenda-wise, just going to give you an outset for how I'm planning on addressing this topic. I'm going to spend a little bit of time up front doing basically level setting and also kind of just making sure we're clear on the question of like why resources matter in Kubernetes. Most people who have done, run their own clusters or run the platform probably have a pretty good idea of what the answer to that is, but I'll tell at least one anecdote that one of my colleagues and I have been kind of using as a basis for putting this together. And once that kind of baseline is established and we've kind of just reviewed real quick resources and limits and the basics, make sure everybody's kind of level set, the majority of the talk is going to be two hands-on kind of live experiments or demonstrations. One on CPU resources specifically and one on memory resources specifically. There are, of course, other kinds of resources in Kubernetes. I think I mentioned them in my abstract. And then when you start trying to trim a talk down to 40 minutes and it's the subject of resources, unfortunately, they didn't get a lot of airtime. They will get mentioned a little bit later. But it's mostly CPU and memory today. And there's a little bit at the end just talking about, okay, great, we talked about some of the, the problems and what happens during contention and so forth, and then just we'll spend a tiny bit of time talking about what can we try and do, what did my buddy Rafa do to try and point everything in the direction to do as well as you can given the realities of the resources abstraction and kind of what's going on there. A little bit about myself. My name is Reid. As was mentioned, I'm up in the Seattle-Tacoma area. I've spent about 12 years plus working primarily with IT automation problems. I've been doing Kubernetes for the last little over 2 years, I guess, now at this point. Prior to that, I mostly worked with Puppet. Love the transition, one declarative management tool for kind of more traditional single operating system Linux stuff into, hey, this is the same philosophy, but it just is more, it's more, what's the word where it means stuff doesn't change? I can't remember it right now. But enjoyed that. Outside of work, I think you were going to, immutable. That's what my brain was going for. Outside of work, I like to do a lot of hiking, a little bit of mountaineering because Seattle is just a beautiful area for that. Try not to work too hard. I'd recommend the same. So getting started, the Kubernetes resource abstraction. Again, the level setting. Resources in Kubernetes are things like CPU, things like memory, things like ephemeral disk. That's another built-in one. Things like GPUs, not a built-in one, but it's the most common one besides those. And in Kubernetes, the idea is that nodes have resources. Pods to run, they need some of those resources. And your cluster is a whole giant collection of nodes, and Kubernetes' job is basically to figure out how to put pods on those nodes in such a way that all of their resource requirements are satisfied. So a little bit about, great, that's what it is, but question, why does it matter? Or sort of why is it worth kind of putting together a giant talk about? I say giant, it's 40 minutes. So story time. At Stormforge, I work closely with a friend and colleague. His name is Rafael Brito. And in 2016, he was tasked with leading a team at a large bank to implement a new Kubernetes platform. This platform was to serve a wide variety of internal customer teams. Rafa's responsibility was to provide the platform, but he wasn't the guy who was going to be responsible for running most of the workloads directly. Again, lots of individual people. He's just the platform manager. So this being early days for Kubernetes at the bank and him still figuring out how all this stuff works, his initial strategy for dealing with this idea of resource requests was pretty simple. He called it benign neglect. He figured that what he would do is he would use some built-in resources to try and point his users on the path on a path rather, by providing or suggesting some generous default request settings for CPU and for memory, and then step out of the way and let the developers figure out and manage and maintain kind of their own resource request settings all by themselves. Mind you, this was early days Kubernetes. It was not on a cloud. It was on-prem. And so auto-scaling wasn't really a thing. And clusters capacity had to be pre-planned to some degree and rationed. OK, so he onboards the first few teams. Shockingly, within a couple of days, this is like not even the whole set of customers, just the first kind of the pilot teams, as you will. Within a couple of days, he started getting calls from people telling him that, or complaining that their pods weren't being scheduled due to a lack of resources, specifically mostly CPU resources. So he went to talk to his VMware team providing the nodes. They told him that he was averaging about 15% CPU utilization across the entire cluster. I think I've actually talked to a couple of people over the conference who told similar stories. I think 10% was sort of the number that I mostly heard. So 15 was actually, Rafa was doing pretty good. But in 2016, Rafa's policy of benign neglect had revealed one of two major problem categories that come from poor resource management in Kubernetes. In this case, it was cost from over-provisioning of resources for the workloads that you're running. The other major category of problem from poor resource management is under-provisioning. Arguably, that one's worse. Under-provisioning would have likely shown itself up in the form of poor reliability or unpredictable performance of the workloads that he was running. So he kind of got lucky with cost. It's expensive, but at least things were working. Not that everything was working because you couldn't schedule all the workloads. But moving on. So that's kind of that's one story. Almost everybody I talked to about this who's been doing Kubernetes a while has a version of that of their own. So it's not an isolated problem. But I wanted to give kind of at least one for people to latch onto. All right, so diving into resources, now that we know that they're important somehow for a couple of reasons, cost or reliability, most of the slides I put up are going to be talking at one of a couple of levels of abstraction here. I've labeled them the Kube API, so the user-facing abstraction for requests and limits, the stuff that you see in YAML for the most part. I've labeled one kubelet, but really this is just nodes. Okay, great, a workload got to a node, or how did it get to the node based on resources? This basically relates to pod scheduling. And finally, I've labeled one of the layers C group, or C groups. This is basically, okay, great, the workload is running on the node, but it's going to have some implementation of that abstraction, and it turns out for CPU and for memory, it's basically all C group style stuff, and so sometimes when I'm talking about what's going on, it'll be at that level. There's a process running, it's on Linux, it has a C group, and so forth. Final bit of level setting, resource basics. Again, reminder for anybody who hasn't seen it, requests are the minimum resources a container is asking for guaranteed access to, and that is an input to the scheduler. It's going to try and find those requests somewhere across the cluster. Limits are a maximum that a container should be prevented from exceeding in the event that it tries. The two are not the same, so just wanted to emphasize that. And as I said earlier, requests are the one that matter in terms of allocation per the scheduler. The scheduler is going to try and make sure that it puts workloads on nodes in such a way that it never exceeds the node's total capacity. If a node has 2 CPUs, it's never going to, the sum of requests of pods running on that node are never going to exceed 2 CPUs. Scheduler never over-provisions, according to requests. Over-provisioning, and I'm kind of getting into over-provisioning because resource management is really simple if you never over-provision. So that's mostly what we're going to be talking about. Over-provisioning is technically possible whenever the requests and limits aren't equal, including when limits are not set. And for many workload types, including Rafa's earlier on, over-provisioning to some degree, for most workload types, there are exceptions, is usually desirable for cost optimization. So the focus of the rest of the kind of the presentation and the demos is going to be talking about like how to over-provision. Should we over-provision? Should we not over-provision? When and why? What happens when you do? The reasons are, over-provisioning leads you towards some savings on cluster costs, but you're basically getting that by sharing resources to a degree in terms of who they've been allocated to. The other flip side is reliability. That's great. Resource exclusivity is the kind of the far end of that spectrum, but that costs. It can potentially cost quite a bit, and money has gotten very expensive in the last few years. So last slide before we kind of dive into a demo and start focusing on this question, is over-provisioning safe? What are the consequences of over-provisioning for CPU, and what are the consequences of over-provisioning for memory? I think that's about almost it for me talking without actually showing anything. So there's a couple of different ways to do demonstrations or philosophies. I think in the talk before mine, Tyler started by saying, here's what I'm going to do and what I expect to see. And then he did it. I'm going to do the flip side. I'm going to run an experiment without necessarily telling you what I expect to happen up front. Feel free to kind of make your own guesses as we go. After it's done, I'll explain what happened and sort of what went into it. But I noticed in the last talk, there's 2 philosophies here, and I've definitely chosen the opposite one. We'll see how this goes. So my lab environment is Minikube. It's running on my laptop. At least I hope it's still running on my laptop. I'll tab over in a second. We'll find out. And I've got a monitoring stack because I want to show you guys actually watching what workloads I have running and what resources they're using as I do it. And I've also got a dedicated node to run these resources on. This is important because I can kind of force exactly the resource contention and allocation situation I want. In a real cluster, this is a complex system. You don't often get to force everything into kind of a magnifying glass and see it as where you want to see it. So that's one note is I'm showing everything in a microcosm, but when you blow this out into a complex system, the interesting thing is you can't really predict exactly what's going to happen all of the time. Can this still work? That still sounds like it's working. Excellent. All right. I also wrote myself a little driver script because I'm terrified of typing too many kubectl and yq commands. And so what I'm going to do is I'm going to do go run /demo.go. I'll show you what it does for me. Help file. I've written out a bunch of different steps. I'm going to start by basically walking you through the inspect nodes point to just prove what kind of cluster I have running. Actually, let me clear that out first. So I have a demo cluster. If I run kubectl get nodes, I'm going to exclude my control plane node, which is running my monitoring stack as well. And we see the one node, demo M02. That's my test node for workload clusters. It's ready to go. Because I'm talking about resources, I want to show you how many resources this node has. I'm going to show you allocatable and capacity for this node. Capacity is basically the raw measure of this node's resources. It's got 2 CPUs, about 8 gigs of memory, and I'm going to ignore almost everything else for the purposes of this talk because I'm already 25 minutes in. And actually, no, I'm not. I started at 6:15. Okay, whew, I'm going to slow down. We're fine. All my practice sessions, I started on the hour. So capacity. That's the raw resources the node actually has. The difference between capacity and allocatable is the node typically kubelet reserves a little bit of capacity for itself and for potentially other system level resources so that when workload pods get scheduled onto it, they're not going to be interfering with that sort of like reservation slice. Allocatable is therefore typically different than capacity. This is Minikube and a dedicated worker node. I realized after I put the talk together that Minikube doesn't do that. Minikube is basically just giving the entire capacity available for running workloads as well. This is bad. I'll explain why when we get to the memory demo. All right, so that's just kind of an overview of the environment. So I mentioned, let's see, that's the overview. Moving forward, experiment number 1, focusing on CPU, resource settings, and CPU contention. Again, we'll do something interesting and then explain the results. So for the CPU demo, I'm basically going to start by loading up some resources. I also realized watching Tyler's demo that I should probably learn K9S. I don't operate that way. I just run kubectl commands. Maybe that's weird. I don't know. I should do a poll. Seeing some head shaking. That's good. So I've got a directory full of resources, CPU. Basically, I'm going to create a couple of services because I got to talk to them and 3 deployments. The first deployment is what's called a best effort workload. It has no requests and it has no limits. Second deployment is one I called requests with no limits. So it's a burstable workload. And the last one has requests, but it also has limits. They're not equal, so it's not guaranteed. I'm not going to talk a lot about quality of service stuff till we get to memory, but just a tag in your head if you're familiar with that. So they should be running by now. We can see that they are. They're all up. Just to confirm, they're all running on the same node. This is important for the sake of the experiment in doing science, because if they were on different nodes, this would not be very interesting, or at least I couldn't force contention. And then I said some have requests, some have limits, some don't. Let's take a look at what those are. A lot of these commands, by the way, I've said I script it because that's way too much YQ. I don't want to show you all of the YAML, but I do want to show you the actual YAML. So here we go, kubectl get pods, and then I'm just going to ferret out just the resource requests for this thing. So there's that best effort one. It's got no requests for CPU, as expected. For the ones that have requests, they're both requesting 500 millicore, and the last one has a limit set of 1 core. I promise I won't keep it all CLI and YAML, so the next piece will actually take a look at a graphical interface. I'm going to show you the monitoring stack so we can kind of watch the consumption of these as we go. I got to start that port forward. So let's run that down here. That's forwarding. And then this URL is what I want to take a look at some workloads. All right. I think Tyler also mentioned Grafana and Prometheus, cAdvisor, wonderful tools. Almost certainly heard of them if you're using Kubernetes. At this point, if you haven't, definitely check them out. This is, let's switch over to CPU. This is basically just a page where I can see how much CPU these workloads are using and how much memory they're using on this node. They're currently using next to no CPU and have a baseline set of memory requirements. These pods, by the way, are a tool called Resource Consumer. Resource Consumer is a part of the Kubernetes project. It's used for testing. I assume because kubelet cares about resource usage. I actually don't know what they use it for. I just know what I use it for. And what it lets me do is it lets me tell these pods exactly how much CPU and memory to consume, just kind of on a whim. Before I switch over, I'm going to try something. I'm going to switch this to just the last 2 minutes because we're going to be looking at really close events here. So the next thing I'm going to do is I'm going to load these things up with some CPU usage. Every single one of these pods is going to have a baseline consumption of almost half a core. Again, the node has 2 full cores available. Those are the curl commands, but basically it's 450 millicore baseline consumption for each of these. So we can immediately over in Prometheus see that consumption begin. So total CPU usage over here is about 1.4, and I've got a stack chart showing each of these workloads. So they're each consuming right around 450 millicore. No contention so far. They're all under request if they have requests, and the node has available CPU. Okay, let's make something interesting happen. What I'm going to do is I'm going to have one of these containers start over consuming. The one that has no limits, I'm going to ask it to consume an additional 2 full cores of CPU. Remember, the node only has 2 cores, and it's currently already using 1.5 of them. So when this pod starts trying to overconsume, something's got to give. Either it won't be able to do that, or it'll take resources from one or more of the other pods. If it does, which ones it can take it from and how much. I'm just going to fire that off and see what happens. All right, so that's running. And this is refreshing every 5 seconds, but I'll hurry it along a little bit. Okay, so we just saw that consumption start. The blue one on top is the overconsuming node, or pod. As it starts, this will run for about 15 seconds before resuming normal baseline 450 millicore. Note what happened. So this top one, it's consuming up to the node's limit of close to 2. There are some measuring artifacts. If it goes above 2, it's not actually using more than 2. That's just some Grafana and Prometheus summing stuff. It consumed up to 2. And it's only getting about 1.48 itself, though. And while it's doing that, what happened? The pod with no requests at all looks like it's getting a tiny bit of CPU time, but it's almost starved. It's getting very little. The one with requests and limits is actually cruising pretty even at its baseline of 450 millicore. It doesn't really look like it was affected throughout this entire thing. And then 15 seconds over, that overconsumption ended. This blue pod went back down to 450. Interestingly, the one that had been starved actually started overconsuming for a minute. Different workloads will do different things, but note that this one was like, oh no, I didn't have any CPU. Now I'm overconsuming and before leveling out again. Interesting. I'll show one more thing and then explain what was happening. And the last thing I'm going to show is just do something similar, but I'm going to ask the one that has limits to overconsume. This one is limited to 1 core, recall. So in theory, it shouldn't be able to actually get up to 1.5 even if it tries, which it will try. All right, that started. And we can see on the graph something very similar. It's not going as high. It is limiting itself at right around 1, it looks like, during this period. It's still taking it away from this green one at the bottom, the best effort pod, the one with no requests and no limits. And after it finishes, that green one is kind of spiking again before going back to normal. That's the experiment. That is repeatable. It's fun in Minikube. So going back to why this matters, what exactly happened here? What was that behavior, and what can we learn from that or use from that knowledge to kind of inform what we do with our clusters? I'm going to start by deleting all of that because I'm going to be coming back in a minute, and I don't want those eating my CPU. Review. No requests, no CPU time during contention-ish. There's going to be an asterisk on almost every single one of these, by the way, because this stuff is complicated. I'm trying to keep it simple for 45 minutes. If you're using less than your request of CPU, it didn't look like there was any interruption. Not really, even during contention. You mostly got what you asked for. And for one of those workloads, when they got starved, it seemed to overconsume later. So that's kind of the keyword there is this is a compressible resource. If you don't get it now, you might get it later, assuming some is available. That might suck for your workload. It might not meet your service level requirements, but it will happen. So what's going on here? Diving down into kind of the C group level again, C groups is where all of the rubber meets the road in terms of how requests and limits actually are implemented in Kubernetes. cgroup and the completely fair scheduler is the Linux basically process scheduler, task scheduler. I'm not sure what the technical term is, that actually runs processes on the cores. And what it is a proportional scheduler. You can assign shares to any C group that basically say you have this much, this percentage share of the available schedule time in the event that you try and use it. Kubernetes equates, when it does this allocation, it basically says if you've asked for one full CPU, I'm going to translate that to 1024 CFS shares when I implement your container on the node. And Kubernetes is going to assign CFS shares according to the request that you made. If nothing else on the node is messing with C groups, this abstraction model can basically result in, okay, if you said you got one core and there's 2 cores available, that's 50% of the node that's kind of set aside for you. If anything else is making C groups, by the way, and assigning shares, all of this goes to, this is being recorded. It doesn't work. So, quick illustration. In the event that we assign, let's say that you're on a 2 CPU node, and you've got 6 total Kubernetes workloads assigned to this node. 2 of them have no requests, and the other 4 have some level of request. In this case, each of these will assume a number of shares relative to the number of millicores requested. Because nothing else is running on the system with shares, that has an interesting effect of it can actually consume up to, in this case, it's asked for 150, it gets 153 shares. It's actually going to be given priority for up to 284 millicore of CPU as long as these are the only processes running on the node. Because it's proportional. It's not actually about the number of shares of millicore you requested, it's about the proportion of shares you get on the node based on that request. So this is how the C group would kind of, or Linux would decide priority allocation for these processes. The other 2 that made no requests, there's an asterisk here. I literally learned during this conference that it's probable that Kubernetes assigns 2 shares to things that have 0 requests, which is really interesting, as opposed to a flat 0. There's a lot of hard-coded stuff, by the way, in how Kubernetes implements this that you just happen across. I'll mention some more later. Those 2 ones are basically what I like to use metaphorically as they're flying standby. If there's a seat available, if there's CPU time available, they'll get scheduled. They'll do great. We saw that early on when the node had 2 cores and only 450 millicore per process. If there's anybody that has shares is asking for those CPU slots, these guys get basically nothing. That's why we saw that one process that had no requests get completely starved out. This has implications for thinking about how do we assign requests specifically to pods running on a cluster, especially if we're like in Rafa's position and he's got to be telling all these developers what do you need to do. Oops. I'll get to that in a second. I realize I have a slide I forgot. But no requests means no priority, so be careful there. Limits are complicated enough that in a 40-minute talk, I wanted to put a QR code on the screen for an excellent article that talks you through kind of all of the interesting caveats and provisos that come with limits. They basically work. For workloads that are latency sensitive, there's some interesting implementation details that mean that they don't work quite as well as you'd hope, and you can get really poor performance from workloads that are being throttled as a result of the limits implementation. Limits are, again, coming from a C group setting, CFS quotas, but quotas are not evaluated continuously, they're evaluated at intervals. And if you exceed your quota at one interval, you might not get scheduled again until the next interval occurs, which is an unexpected lag time, hence latency issues, and so forth. A lot of cool articles about this. Those articles are all very long. The diagrams are all very complicated. For our purposes, what it really comes down to, though, at this level of talk is we learned that requests are pretty important. If you have no requests, you are basically flying standby. You do not get guaranteed any CPU time at all, especially in the event contention starts occurring on your node. And you're potentially subject to near complete starvation. If requests are all set, you're basically guaranteed a minimum amount of CPU time, the time that you requested. This has an interesting reflection on limits, because what that basically means is limits are often implemented to try and mitigate noisy neighbor issues where one workload could take cycles away from another workload. If requests are all set correctly, you're never going to be able to take away from a workload resources it has properly requested. So they aren't necessarily that critical for noisy neighbor situations as long as requests are set properly. A lot of people will argue and take the position that you just shouldn't set CPU limits at all as long as requests are working. And that's largely the side of the fence I land on, although I'm open to debate if anybody wants to talk about it. All right, so that's CPU. Could put a bookmark in all those memories. We'll talk, dang it, that was an unintended pun. We're going to talk about memory next before we kind of circle back and say, now we've learned a couple of things about these core resources. What do we do with that? All right, experiment number 2, resource settings and memory contention. So we're going to do the same kind of thing. I'm going to go back to the live demo. We still have this kind of observatory running, but I'm going to fire it up with some memory resource workloads. And these workloads I'm going to, well, let's just take a look. Applying a directory full of YAML, a couple of different services for 2 different deployments, one that has best effort, no requests and no limits, one that has some requests but no limits, and one that has both requests and limits. Those should be running. They are. They are both running on the same node, so there is potential for contention. And let's take a look at the specific values they're requesting. We've got, again, best effort, no requests. We've got, for the one that has requests and limits, it's requesting 1 GB of memory. And the next one down is requesting a gig and also limiting itself to 1 gig. This node, recall, has 8 gigs total. We'll start ramping this up in a minute. We'll get closer to 8. We're not very close right now. Let's run those. So I guess we'll go over here first and just take a look at what is going on, switch over to the memory namespace. Right now, the baseline consumption is small, so I'm going to bump that up. It's 85 megs each. Let's bump that up to something more interesting. Oh yeah, in case I wasn't there, I would go there, but I'm already there. I'm going to set it to about 500 megabytes on each of these workloads. In this case, I'm actually just restarting these things with an environment variable to set that baseline consumption. We can see that happen here. Tangent. One of the most annoying things to figure out in this live demo was how to make these queries for Prometheus show only the pods that were running and get rid of the ones that weren't, because CAdvisor keeps them around for about 30 seconds. Sometimes you can see the restart, sometimes you can't because the timing is that tight on the way the metrics work. In this case, you can't actually see them restart, but I guarantee you they did restart. First experiment. One of these things has a limit of 1 gig. What if we take it, this is the request and limits pod, or deployment, and we're going to have it consume an additional gig on top of its existing 500 megabytes for up to 30 seconds. I'll give this one away. It's going to get killed. It's going to get killed real fast. There that goes. Post requests. Refresh this. It starts consuming just a little bit. It's that yellow one. And that down spike, that was it dying. But we can confirm that. We can observe over here. I'm going to take a look at the pods for that request and limits deployment. Note the one restart 13 seconds ago. And if we describe that pod, and I'm just going to grep for the container information here at the very end of the kubectl describe, we're going to be able to see a couple of things. No, I don't need to do that. Current state is started. That's great. The last state is terminated. Reason killed. Another bookmark, memory bookmark, killed. It told us exactly what happened. It was very clear. Love that. Doesn't always do that. We'll see it not do that probably in a minute. I say probably because there's some non-determinism here. Exit code 137. OK. Anybody surprised? Exceeded the limit. It got killed. Cool. That's like the easiest one to demo. I'm going to set up, just to demonstrate, the node has lots of memory. If you exceed your requests but don't have limits, you're not going to have a problem as long as there is memory, although we're creeping into uncertain territory here. So I'm going to ask each of these guys to consume an additional gig. This is the one that has no requests and no limits, and this one has requests but no limits. And visually, we should be able to see that. Here we go. So here's when we got killed. And then now we're having 2 of these pods consuming an extra gig, using 1.5 gigs each for the no requests, no limits, and for the requests but no limits. Just demonstrating that that works, mostly because it means containers running on your nodes can use as much memory as they want if they're not going to hit their limit, if the node has the memory available. So the next interesting question is, what if the node doesn't have the memory available? There's a lot of things that could happen here. I'll explain some of them later, but just to kind of show the simplest one. I'm going to change the baselines here. I'm going to change the one that has requests to request a lot more. I'm going to have it request 2.2 gigs and have it set the baseline to 2 gigs. So it's going to request a bunch and use some, but be within its requests. Should be able to see that. There we go. OK, it bumped up. Now it's at 2.1 gigs, again requesting 2.2. And I'm also going to set the requests for the one that has requests and limits. I'm going to bump its request to 5.2 gigs, set its limits higher at 6 gigs. That gets updated. It's not consuming yet because it didn't change its baseline. It just changed its requests. Just confirm that. So it restarted to get that new request and limits. Now we're ready. Now I'm going to start having it try and actually consume all that memory it requested. But this is going to put it real close to the node's actual limit of available memory. So it's going to try and consume an additional 4.4 gigs. So that started. There's actually 2 or 3 different things that can happen when I do this. It's usually one thing. We'll see if it's the one I expect, in which case my slides will match. But it has happened before that it isn't the one I expect, in which case I'll call it out on the slides. We're climbing, we're rising, we're getting close to the 8 gigs of memory that the node physically has available. And that was actually a lot faster than usual. What happened here? Suddenly, almost everything disappeared. Timing-wise, we can see that there was a slight, this no request, no limits pod actually did get killed. It got killed slightly before the other 2, which interestingly, they got killed too. And looks like we're getting a restart now. So it took a minute, but those containers are running again. That's interesting. One of them's running again. Oh, this is, remember I said it's non-deterministic? This is actually one of the more unusual things that can happen. So there we go. Okay, now one of them's restarted, is using its baseline. There goes the other one. Okay, cool. All right, now we're back to the situation that I expected it to eventually get to. But basically, a bunch of chaos just happened. And yeah, there's only one node running in this cluster, but everything seemed to happen on the same node. And even though some stuff crashed, it stayed on the same node. We'll get to that. But first, I'm going to shut all these down. No, I'm not. I'm going to tell you something about them. This is why I write myself a demo script. There's too many commands. I wanted to take a look at that kubectl describe pod again and take a look at that container status. So we see again, the current state is running. The last state is terminated. Remember I said remember killed? This doesn't say killed. Interesting. But it is exit code 137, which, trust me on this, that's killed. All right, let's talk about what happened and sort of what that means. After, see if I'm right about, I think I do kill it now. Yeah, now I kill it. All right, there it goes. So, the review. If you have memory limits and your container exceeds them, it will be killed. At least that works as expected. Containers, unlike CPU, if a container doesn't get memory that it tries to allocate stat, something's going to get killed. Memory is not a compressible resource. You're not going to have that ability to just do it later in this case. What gets killed and how? That's the interesting thing from a cluster stability standpoint is there's not, if you start running out of memory, this is not great because you don't have a lot of determinism in exactly what's going to happen. So let's talk about what level of determinism you could have and why you don't always have some. Starting at the kubelet. So not Linux kernel at this point, but the kubelet. Best case scenario, if your nodes start running out of memory because workloads are misbehaving, they're over provisioned and the requests aren't quite being honored correctly, is the kubelet might notice. I say might because the kubelet's really only going to look for this kind of thing once every 10 seconds, and oftentimes in this overconsumption situation, 10 seconds is way too big a gap. Another fun thing is what kubelet's doing is it checks every now and then to see if the node's available memory has reached an eviction threshold. The eviction threshold defaults to something tiny. It's like 100 megabytes. If you're within 100 megabytes of having a problem, then it'll start evicting things. On modern nodes, that's nothing. I don't recall specifically what the various cloud providers end up having this set to. I don't believe they leave it at 100 megabytes, but it was interesting to try and experiment with on the defaults. In the event kubelet notices this, it will start performing evictions. Evictions are good because kubelet gets to decide what's the least important workload on this node. I'm going to kick you off, and you're going to go back to the scheduler and get sent somewhere else, probably not here, because I'm going to trigger a condition such as, did I say what it was called here? Memory pressure? I don't think I listed it. That basically says don't schedule anything on me, I've got some problems. That's not what happened in the lab. This was too fast. And I say probably because, again, there's some non-determinism here. Yeah, question. How does it determine least important? So there's a number of factors that go into that. A big one is quality of service. So we have guaranteed, we have burstable, we have best effort. Guess which one of those is the least important? If you have best effort pods running on that workload, they're probably going to get booted. There are other signals you can provide. Off the top of my head, I forget the specifics, but there's basically priority. You can assign pod workloads priorities, and those will also be taken into account in terms of what gets evicted. I don't think that I have used those a lot personally because, like I said, it rarely gets to this point on clusters that I'm familiar with, because what you usually get instead is you usually just reach killing, where kubelet missed its chance, the Linux kernel has stepped in, and it is just going to start taking over and killing things as needed. The interesting thing about determinism here is Kubernetes does its best with various cgroup settings to organize prioritization for the killer, but it doesn't get to pick. The Linux killer at the end of the day is what decides what to kill. Quality of service will have a huge effect on what gets killed first. Best effort stuff basically gets a signal, a prioritization influence to the killer, so it's at the front of the line. Burstable is after that, guaranteed is at the end. But killer also takes into consideration things like how much memory is actually being used by these processes, because my goal is to free up memory. So if it reaches that point, you don't actually get a total amount of control, especially with cgroup v1. I'll mention cgroup 1 versus 2 in a second. But in cgroup v1, there's only so much control that you get. And so if you get to out of memory, that's just bad. Yeah. Correct, yeah, so quick definition. A best effort quality of service pod means that it has not requested any resources and has not set any limits. Burstable means that it at least has requests. It might have limits, but if it does, the limits are not equal to the requests. To get to guaranteed, which is the highest quality of service, that means you're last in line to get killed, you need to request both CPU and memory, and the limits for CPU and memory also both need to be equal to the requests. You can't just do one, you have to do both. Which is interesting if you don't think that CPUs should have limits. It means that guaranteed quality service is kind of out of reach for you, unless you're going to lean into the over-provisioning higher costs. Anyway, we'll get there. So this is probably what happened in the lab. I wanted to highlight the fact that it didn't say killed, because there's a bunch of nuance about what goes on. Long story short, there's some very detailed articles here if you're at all curious about what actually happened that go into detail. But you got to read what sounds like a PhD thesis or the actual code in order to find out like why in this situation does it not actually say killed. All right. So the last summary before we kind of talk about the last piece, that just going to wrap it up. Great, we learned something about requests and limits, but what do we do with that? Memory requests are also very important. Memory isn't guaranteed by request. One of the things I didn't emphasize in that lab test, everything was within its requested memory. Nothing was exceeding its request, but we still got killed. There's some things you can do to configure kubelet so that's less of a possibility, but requests don't guarantee memory, at least today. Because of the consequences, over-provisioning of memory has a higher consequence than over-provisioning of CPU for most kinds of workloads, so maybe we should be a little conservative on the limits there. Limits are more helpful for memory, mostly because it gives you more control over saying misbehaved workloads are the ones that should get killed and not the ones that are potentially minding their own business but have a noisy neighbor situation. Last note before we move to the last section. Everything I just talked about is true when you are running on a Kubernetes cluster on an OS that uses cgroup v1. cgroup v1, cgroup v2, it's the same basic system, a few differences. cgroup v1 has some terminology changes versus 2 in terms of CFS. So CFS shares, like I explained earlier, is changed to CFS weight. It's exactly the same thing, basically, but different nomenclature. I found shares kind of confusing. I found weight less confusing. I don't know why they made the decision to change it, but that's one note. Memory gets new controls. Memory gets new controls that actually help you better say things like, if you are under your requests, you should not get killed. The killer should go after everyone else but you, which is not true on cgroup v1. So there's more determinism in v2 once we get there. I showed v1 because most of the major cloud providers aren't using that by default yet. But I get the sense that we're very close. Minikube is usually able to do that. So just a note on that. Finally, a call out to other kinds of resources. We talked about the abstraction. The abstraction is what Kubernetes is trying to present for lots of things. The built-in ones are ephemeral disk, memory, CPU. It's commonly seen these days to extend that to GPU, but it's a general model. You could, in theory, extend it to almost anything else if you wanted to, as long as you provided the implementation for it. I won't talk a lot about it right now because we're almost out of time, but just wanted to call out it is a generalizable abstraction. So, back to Rafa's story, like what do we do? Okay, we understand, we understood conceptually before that that over-allocation on nodes was gonna cause some pain. Now we have a little bit deeper understanding of what actually happens when that goes on. what do we do to try and influence our users of Kubernetes platforms to work on this, or what can we do to kind of maximize our stability and resiliency in our clusters in terms of resource requests? Sorry, it's kind of hard. As the ecosystem matures, there are other options, but we'll start from where Rafa did. Most people that I talk to about this, who've used Kubernetes for a while, they typically start with, I think I was actually talking to somebody before this talk, when you start introducing people to Kubernetes, you might not even mention requests, because you don't need to set them to run a workload. So you might end up with a lot of pods and best effort. I think the guy, Tyler, on the talk before mine, Tyler specifically called it out in one of his slides. You end up with clusters all the time that have tons of best effort pods. So you don't bother setting them. But at some point, that's going to fall down. You might start getting some performance issues. Your cluster doesn't scale well. You realize you got to set something. Stage 2 at a large organization is you say, everybody's got to set requests, but you know what? You don't have to think too hard. T-shirt sizing. You either choose small, medium, large, and that's good enough, and away we go. That tends to change when the cost pressures from that still ends up resulting in largely over-provisioned clusters. When the cost pressure from that comes down from the top, people typically advance to something else. Stage 3, manually tune every workload, whether, usually it's pretty irregular, and it's based on signals like, oh, this one's getting killed, or this one's getting throttled, or this one's showing up at the top of the list of the most expensive workloads in the company, in which case you should go take a look at it. But it's largely manual on stage 3. Through all of those stages, options that are out there to try and help your organization do well at this are basically, there were some excellent presentations. The presentation before mine did a good job of running over a lot of options for this. It's basically about creating policies, including policy as code, that can influence developers or application owners' behavior to guide people into paying attention like Rafa wanted to. He said he wanted to point people down the path of getting it right. There's built-in resources called limit ranges that you can use to ensure things always have requests, even if they're just kind of dumb defaults. There's resource quotas that can be used for if a group, like one of Rafa's customers back at the bank, had overconsumed themselves, they might be forced to stop and take a look at their allocation before continuing without affecting others if they had a quota in place just for their application. Tools like Caverno can be used to define much more granular and specific policies that, again, the objective is to influence user behavior on Kubernetes and kind of force people to invest time and effort in looking at their resource requests. If you're going to do that, it is really important to have some kind of tooling that helps them be successful with that. Even the little Grafana that I was running is something that can really help. Is you know that you're going to set requests according to what's actually being used, but you got to be able to tell what's going on. So any kind of tooling that actually helps people understand that would be pretty important. The last thing that we're seeing more recently, oh, there will be a shameless plug for my employer at the end of this, is try and automate this. A lot of it are things that in theory, we should be able to have machines help us do, if not do absolutely for us. So how would that work? Ideally, a tool would, so the VPA, the vertical pod autoscaler, is an example. I would say it's not a very mature one in terms of its full set of capabilities, but it's an example of something. It should be able to observe and collect utilization data from workloads, calculate and generate tailored request settings for all of them, and then automate actually managing that in production. This article is something that is part of what forced me into giving this talk, honestly, was basically talking about the premise of the developer experience regarding it. It doesn't provide a solution, but it kind of talks about the problem more in depth. This is the shameless plug. The reason I get to spend all this time sort of digging into these details is I do work for a company that's trying to create exactly that sort of automation tool. We're not the only one. There are others. This is my favorite. So if you're at all curious of sort of other ways to do this, Rafa didn't have tools like this in his day. He had to kind of go the route of trying to influence his application owners and developers to do it themselves. But I firmly believe that whether my company Stormforge does this or somebody else wins out, or if there's an open source project that gets good enough, this is likely the future of resource management in Kubernetes, unless there's some insurmountable, intractable problem that I have not seen yet. Because there's way too many workloads. It's way too hard for developers to manually tune all of this, but it is really important for stability and reliability on clusters. I do think automation is where this will eventually end up. Not sure when we'll get there. With that, I've almost hit my timing. I don't think I've run over too far. And so feel free to connect with me on LinkedIn. I'm happy to. I'm a terrible LinkedIn person. I don't chat very often. I don't look at things, but I do promise to try and be more engaged for a little while after the conference if anybody does want to just talk about any of this stuff. There is also a link to, if you want to try my employer's free trial product, there's a link to that. And otherwise, we're open for any questions people may have. There's a lot that I didn't touch on, so feel free, if even the question wasn't directly addressed to something that I said in the talk, I'm happy to try and tell you what I think about it, if anybody wants to go take particular direction. Yes?
Okay, see if this works. I was wondering if there's any way that you can provide back pressure to the process in the container to free up resources that it is using. So we have a monitoring pod that when it gets a lot of logs coming through it, it blows up and gets really big and takes up a lot of memory. But then when the traffic falls off, it doesn't free up its memory. It keeps it, happy that it's got lots of memory. This is all within the limits that we've set. And is there any way to have Kubernetes reach in and say, garbage collect, you idiot? And
garbage collect, you idiot. I like that. So I'll mention first one thing that I'm aware of. I don't think it's a direct answer to your question, especially depending on the application, like if it's Java or something. One cool thing about the cgroup v2 implementation is there is an additional control where if a pod starts exceeding the memory it's requested, the operating system will start giving a little bit of pressure to try and free up some of that memory. I don't think that'll necessarily work for maybe, I don't know what the application stack was that your application uses. Say again? Vector? Sure, yeah. I am not aware of a Kubernetes mechanism to do that. If you didn't catch the talk before mine, that might be of interest. Tyler did an overview of a lot of tools related to this general idea of I want to do things like redistribute resources. He mostly talked about things on the pod level rather than the resources in the pod level. So I don't have anything that comes to mind myself, but there was some very interesting things in the previous talk. If you see it's ballooned to the limit. Yeah, okay, so if anyone's watching the recording, the question is basically, if we see it doing something, is there any way we can go in and sort of change its limits or requests and kind of force it to So when you say change limits or requests, my mind goes to the actual resources. There is a notable thing that's in alpha right now called in-place pod resizing. It doesn't get you what you want, but that's the only way to change limits or requests right now. At the moment, to change actual limits and requests, the pod is going to die. Like the pod has to get restarted.
that would be the idea, but it can restart quick enough so that there's not a noticeable gap in the log.
Right.
Not at the limit.
Yeah. Short of general Kubernetes solutions like sidecars that actually just sit there and watch for things like that, I don't know of any tools that specifically would address that. It does sound like an interesting use case, though. Also an interesting idea of solution to go straight to, if it's over-consuming, let's just shoot it. I kind of like the aggressiveness.
Any other questions?
So for those of us who still have to do this manually, one of the things we discovered early on is, when nodes start running out of memory, things get unpredictable. Sometimes the thing that the kernel decides to kill is something important to the stability of the entire node. Rarely, but it would happen. So our solution to that was limit ranges have a feature in them. You can set the ratio of what the limit to request ratio is, and it can't exceed that. So we've basically made the requirement for memory requests must be the same as limits to prevent that kind of situation. Is that something you've seen other people do, or is have you seen other strategies to kind of address that kind of situation?
Yeah, so I think that's a great example of, it's using limit ranges specifically, but it's one of those like policy as code to kind of choose force people into a certain behavior. We have seen people who do basically exactly that, who just force memory to be have a 1-to-1 ratio. How they do it varies. Limit range is one thing. Conferno can do similar things as well. It's tricky because on the one hand, I say tricky because in terms of knowing when you need to increase, well, actually, the more I think about it, there's not really any super downsides to that, except you're not going to be able to over-provision at all. But yeah, we have seen other people doing that, for sure. And that avoiding the chances of killing something important is a good call out, especially if there's any sort of non-determinism. It's one thing to kill a neighbor workload, but it's something else if you accidentally kill something critical to the system, like kubelet.
I was curious if you could, this might be a more basic question on Kubernetes, but you touched on like eviction. So when a process gets killed off and it gets sent over, I guess, or rescheduled perhaps to another pod. Like how fast is that? Is Kubernetes like pre-seed all pods with all possible containers, or is there some memory copying that happens, like network transfer?
So working backwards, Kubernetes does not by default magically seed all pods on every node. It sounded to me like you're talking about like fetching images, like is it ready to start on another node immediately? Potentially no. There's absolutely no guarantee that it's doing that unless you've set that up yourself in your cluster. So if something gets evicted, from memory, I don't recall if it honors any sort of graceful, like does it give it a grace time as it shuts down to like gracefully close? It might not. So now it gets sent back to the scheduler. The scheduler is going to try and place it as fast as it can. That works as fast as it works for anything in your cluster. But yeah, if it lands on a fresh node that doesn't have the image, it could take a little while for anything that gets evicted to actually spin back up again. It's still better than just a random kill, but.
Any other questions? I can think of one. I see here that you've got a solution that tries to automate the setting the resource demands, but how does that work? Is it entirely based on assuming that future behavior will be pretty similar to past? A second question to that is there anything that solves the problem of, you're planning on having users give themselves their own labels for what the demands are? How do you keep people from being pigs in the organization and just saying, I want the max all the time if there's no cost back pressure on them?
Yeah. So again, working backwards, cost back pressure, especially in large organizations, most organizations that I've worked with who are like an enterprise scale do have something in place to do some cost back pressure. Some of the organizations I work with, though, especially if the organization has a lot of money and whatever they do is very important, like the best back pressure we've actually seen is, because typically the application owners are not the ones who are experiencing the pain of this. It's usually the platform owners. The platform owners are often just looking for any way to, as you said, give back pressure to the application teams. Oftentimes, it's just showing them that what they've requested, if to say how do we prevent them from like just asking for too much? One of the best ways is to have a clean and easy way of showing them that what they've requested isn't actually being used. Visibility, transparency is one of the only things you can do if there's not any other direct costs there. But we're kind of talking about a people problem now as opposed to a technical problem, which working backwards on your question again, the people problem thing. I think automation tool, in terms of like how does an automation tool handle this, I want to call it first that the objective is to reduce load on people. And so an automation tool is typically going to work pretty well for like 80% of workloads. There's likely to be a few workloads or a few circumstances like Black Friday's coming up, and there's no way that we could have predicted that by looking at the last 2 months worth of data, where somebody's still going to have to step in. But any automation tool's job should be to try and reduce the amount of work that people do to only exceptional circumstances as opposed to everything. The way that our particular tool works is it is we observe about a month's worth of data every time we generate a new recommendation. There are some ML algorithms that do have forecasting and concepts of seasonality. They can tell that your workload is busier on Monday versus Saturday and stuff like that. But outside of you'd have to have user inputs or policies that say things like this workload needs to be as reliable as possible versus this one you can maximize for savings. It's a complicated, it turns out the answer to your question is slightly complicated. But an automation tool, in addition to just forecasting, ideally should be responsive. It should address things like, oh, this thing just got killed 5 times in a row. I think it might need something new, even if its forecast, its previous data didn't show that. I think you might have asked more, but that's all I could remember.
Okay, last call. We might have time for one more question if there is any. If not,
One thing you just briefly touched on was auto-scaling. And I could imagine a scenario where with requests and limits, you're sort of restricting supply, but of course the horizontal pod autoscaler is going to try to increase demand based on possibly a different set of metrics. Seems like you might get, just maybe you could comment on how autoscalers and those things kind of work together.
So auto-scaling, and specifically horizontal pod auto-scaling is what I'm hearing, because there's 3 different core means of auto-scaling in Kubernetes. So what we were just talking about is the individual requests and or limits for a pod, but when you have a horizontal pod autoscaler in place, its job is to try and make the utilization, oftentimes, there's other metrics, but oftentimes match some ratio against the requests that have been configured. In the event that you want to do multiple things, where you want to say, great, I want the horizontal pod autoscaler to be working, but I also want to pay closer attention to this individual pod's resource request and or limits. That's I think mostly what that keys, the first place my brain takes me is remember that the VPA project, kind of the existing standard public one, specifically states that because of potential tension there, like it doesn't play nice with horizontal pod autoscaling. You pick one or the other. You don't have to. Commercial products, the ones including StormForge and I'm sure others, do vertical pod autoscaling in conjunction with horizontal pod autoscaling. It's an interesting problem because either you just preserve the shape of the existing behavior when you start vertically sizing pods, in which case you have to adjust the horizontal pod autoscaler's targets, or you have to start getting a little bit more, now I'm speculating as opposed to talking about built software, or you have to start changing what those metrics are depending on the number of pods running. Like maybe if there's more pods running, you're more okay with having those pods more saturated, as opposed to if there's only a few running, you need to have more overhead. Mostly, I think what that all that response tells you is that that's a complicated, interesting question. But you knew that.
okay, thank you, Reid. That was a great presentation. Please join me in thanking.